let's look at some aspects of electromagnetic waves. So for one, like any waves, electromagnetic waves travel, they carry energy, and they are cyclic or periodic. Here we have demo of various waves. This one is labeled water wave at the top, then we have a sound wave and an ether wave. So I'm going to start this demo, and I would have to thank my daughter for turning the crank in the back so that the demo would work. So you see that if you're following the water wave, each of the particles along that water wave travels on a circular path. If we follow the sound wave, we notice that each of the particles on this sound wave travel back and forth along the direction of motion of this wave. And then if we look at the bottom wave, each of these particles moves up and down perpendicular to the direction of travel of the wave. So the top one is a water wave. It has a more complex motion than the other two. The sound wave is a longitudinal wave because each of the particles moves back and forth along the direction of motion of the wave. And the bottom one used to be called an ether wave when this demo was created. And that is because they thought that since sound and water needed a medium to travel through, light would also need a medium through which to travel. And they thought that that medium was ether. Well, Michelson and Morley showed that ether does not actually exist. And now we know that light and electromagnetic waves travel through vacuum just as easily as they travel through other media. Actually, they travel more easily through vacuum than they travel through other media. So we now know that light, which is an electromagnetic wave, can travel through vacuum, which is a good thing for us because that's how we get energy from the sun. The sunlight travels through vacuum to make it to us so that life can exist on Earth. Now, as I said before and as you saw in the demo, electromagnetic waves are transverse waves because the particles on the waves oscillate perpendicular to the direction of propagation of the wave. And we also discussed the fact that they do not need a medium through which to travel. Now, electromagnetic waves are clearly made out of electric waves and magnetic waves. So the electric fields and the magnetic fields oscillate perpendicular to one another, and they have the same frequency. Furthermore, the electric fields and the magnetic fields of the wave are in phase with one another. So they oscillate with the same frequency and in phase with one another. So here we have a little segment of an electromagnetic wave. The red wave, let's say, is the electric field. The blue wave is the magnetic field. And you see how the electric field is perpendicular to the magnetic field. They are traveling at the same frequency. They are in phase with one another. We can see that in this little video here. So I said that the electric field is red, magnetic field is blue. And it turns out that the electric field and the magnetic field are perpendicular to the direction of travel of the wave. So that direction is given by the right-hand rule. You place your hand in the direction of the electric field, bend your fingers in the direction of the magnetic field, and your thumb will point in this direction, the direction of travel of the wave. Now, here in this little video, you see that there is one electric field that is up and down, and there is one magnetic field that's in and out. But if you actually looked from the side, so if you had the electromagnetic wave coming at you or going away from you, you would actually see something like this, where the electric field has different orientations and the magnetic field is perpendicular to those orientations. So you don't just have one single electric field, one single magnetic field, but a big combination of all. Now, we will pay more attention to the electric fields in another video, because when we are able to just orient the electric field in one direction, we'll say that that light is polarized. This particular light is unpolarized. but like I said, we will talk about this in a different video. The speed of electromagnetic waves in vacuum is c is 3 times 10 to the 8th meters per second. Not quite that much, but that's a very good approximation. And any wave has two properties. One is the wavelength, and the other one is the frequency. And the product of wavelength times frequency gives us the speed. Now, wavelength is a distance. Frequency is 1 over period. So essentially what this equation says is that speed is distance divided by time. Now, since electromagnetic waves travel with this speed, times 10 to the 8th is the important part here, then there's a really large range of frequencies and wavelengths that multiply together give us this value. Based on that, we can talk about the electromagnetic spectrum. So here is the electromagnetic spectrum. Across the top, I have frequencies. Across the bottom, I have wavelengths. So here I have 10 to the 4th hertz, 10 to the 8th, 10 to the 12th, and so on. And remember that I have to multiply the frequency by the wavelength in order to get the speed of light. So then if I have 10 to the 4th here, I'll have 10 to the 4th there, 10 to the 8th, 10 to the 0th, 10 to the 12th, -4, 10, 16, -8. So the product of those will give us that power. So let's look at the different ranges. In this range, we have what we call radio waves. And those are subdivided into AM, that stands for amplitude modulation, FM, which stands for frequency modulation, and then at a higher frequency are microwaves. Now, an interesting fact about AM and FM is that FM waves, they have a lower wavelength than AM waves, and higher wavelengths, longer wavelengths, bend better around obstacles, which is why we can hear AM radio stations from very far away. The signal is not excellent, but we can still hear the radio station, whereas for an FM radio, we need a line of sight path from the radio station and our radio, our antenna, to get a good signal. All right, then at higher frequencies, we have infrared. Then there is a very narrow band here for visible light. Then we have ultraviolet, X-rays, and gamma rays. So since energy is h times frequency, h being Planck's constant, f is frequency, we'll talk about this in a later chapter. But since energy is a function of the frequency, then the more frequency there is, the more energy there is as well. So gamma rays are just high energy light, essentially. All of these are light, but they have different amounts of energy. So this is the lowest energy, that is the highest energy.